All right. So let's get started here. We're going to pick up with where we left off last time, talking about kinetics, right? So this is how the concentration of species in a reaction will change over time. So here we have this reaction between hydrogen gas and iodine to produce HI. And we're looking at a plot here where we have concentration versus time. I'm going to tell you that one of these curves corresponds to the concentration of hydrogen as it changes over time. And the other one corresponds to the change of hydrogen iodide over time. All right, and so let's try to figure out if we can identify which one is which here, the green or the red, which corresponds to hydrogen and which corresponds to our product here. So what do we think? So let's take a vote here. If we're looking at this red curve here, do we think that's the hydrogen or the hydrogen iodide? Raise your hand if you think it's hydrogen. And what about HI? Excellent, right? Because our product will increase in concentration over time, right? So the red curve is increasing over time. Whoop. Boom. And our green curve is decreasing over time because reactants are consumed. That was terrible, but yes. Okay? So from these curves, concentration is something, generally speaking, that's very easy to measure over time, right? So we can create a plot like this, and from this plot we can analyze our data to figure out rate. Okay? So there's two ways to do it. One would be kind of like the quick, dirty way where we can do it using pencil and paper, finding what would be called the average rate. And that's something that would have been easy to do even like back in the day with their graph paper and stuff like that before chemists had computers, where you simply calculate the slope of this curve using rise over run, right? So I would just take two of my data points here. I would measure the distance between them on the x-axis and the distance between them on the y-axis. The average rate would then just be equal to rise over run, right? So in this case, the change of concentration of H2 over the change in time, okay? But remember, rates we always report as positive values. So since my concentration of reactant is going down, what am I going to have to do to this value here? Just multiply it by a -1, right? Just to flip it to be a positive value. Because when I calculate that change in y, I get this negative value, but again, we're going to report rates as positive numbers. Okay? So that we could do just like with graph paper and sort of measuring the distance between these points. Nowadays, of course, we have much fancier sort of calculators, computer programs that can actually use calculus to calculate what's called the instantaneous rate. All right, this is not something that we can do just on pencil and paper or by looking at data. We would have to have some sort of a fancy computer program or at least be in a higher level of math to do it. But if we were to calculate the instantaneous rate, what we would do is for each one of our data points, so let's look at a data point on our red curve here. Right, if we did some calculus and did the slope of this curve, the instantaneous rate would be if I took a tangent line to this point. Let me actually make it a little bit clearer even. Get a bolder color or bolder line. All right, so the slope of this tangent line to my point That would be the instantaneous rate. So this is something that you would be able to do in the lab, for example, by entering your data into a computer. Not something that we would be doing here in lecture, but just to kind of sort of make sure it's clear for if you guys do get to that in lab. Our instantaneous rate would be the slope of the tangent at each point. Okay? And regardless of which way you're going to be measuring this, for this particular reaction, what's happening to the rate of the reaction over time? Is it increasing or decreasing? If we look at the slope of this red curve, if I start putting in tangent lines, right? Let's look at this very first tangent line here. Okay, and then let's go to the other extreme. Let's look at the tangent line on the other end of the curve, where it's nice and flat. All right, regardless of which way we measure this, either average rate or instantaneous rate, we can see that the rate of the reaction is decreasing over time. And in particular, what's always true, regardless of the order of the reaction, is that initial rate is the fastest. Right when you mix those reactants together, that's when your reaction is happening the fastest, but reaction rates are dependent on concentration, and so it will decrease over time. Now, for a 0th order reaction, it's independent of concentration, so it will remain constant, right? But that initial rate is still going to be the largest value that you get regardless of order. Okay, I guess it might be the same for a 0 order, but for any 1st order, 2nd order, the initial rate is always the quickest, and that's what this curve shows here, right? So typically in the lab, what you can measure very easily is concentration as a function of time. You create a plot like this. You analyze the slope of that curve in order to get the rate of the reaction. All right? And we talked about how reaction rates, they fit nicely into these equations. Well, not this. Hold up. Not there yet. Where the rate is dependent on some constant times the concentration of reactant raised to some power. And we called this the order of the reaction. All right, so where we left off with last time was how to take some rate data and use that to figure out the order of the reaction as well as the rate constant for that reaction. All right. And we did this by this strategy of taking 2 data points and taking the ratio of those data points. All right, so that's all well and good when you have one single reactant, but that's kind of rare. So let's look at another reaction here. Same sort of data. We have this initial rate data, but now we have 2 reactants. We have nitrogen dioxide combining with carbon monoxide to produce nitrogen monoxide and carbon dioxide. So now we have 2 reactants to worry about. Okay? So when we construct our rate formula here, it's going to be the same idea, but with 2 reactants. So my rate is going to be equal to some constant times the concentration of my first reactant, the nitrogen dioxide, raised to some power, the order of that reaction. But now I also have my second product, so I'm going to have to put the concentration of that, my second reactant. So I'm going to have to put the concentration of that second reactant in my rate equation as well. Okay, so looking at this rate equation, now we have these 2 rate orders. So I use different variables, right? M and N. We would say that M is the order with respect to my nitrogen dioxide, right? Because that's what I'm raising to the power of M. N is then the order with respect to my carbon monoxide, right? Because I'm raising the carbon monoxide concentration to the power of N. And my overall order is equal to the sum of M plus N. All right, so sum up all those exponents and you'll get the what's called the overall order of your rate equation. Cool? All right. Now, again, our goal is going to be the exact same. Our goal is to figure out what M and N are. And once we do that, once we establish what our order is with respect to the nitrogen dioxide and our order is with respect to the carbon monoxide, then we can plug in our data and actually figure out what K is as well. We got to figure out what those orders are. We got the same type of data here, all right? But now, of course, again, now we have two columns for our initial concentrations. And we're actually going to play the same game. We're going to pick two data points and take the ratio of those two data points. But we have to be very clever about which two data points we pick, okay? I want to pick, and I'm going to tell you right off the bat, I'm going to pick this one here and this one here. All right, and I'm going to make our math even prettier here. Hold up. Okay, and the reason that I'm picking these two data points is because the concentration of one of these two is changing, but the concentration of the other one remains the same. All right, so we're going to be clever and we're going to pick two data points. One where one of our reactant is indeed changing, but the other reactant is remaining constant. Okay, so let's see why we're going to do that. Let's play the same game we did before. We're going to take the ratio of these two data points. Right, so the rate of data point 1 over the rate of data point 2 is going to equal all this business for the first data point, K, times the concentration of NO2 of my first data point to the power of M, times the concentration of my second reactant, but still that first data point, divided by now this same expression, but I'm going to use the values for my second data points. Let me use a different color to indicate my different data points here. Used orange, I'll do orange again. Okay? Now, remember our strategy for taking the ratio was I got to get rid of this constant that I don't know in this equation. Right? So by taking the ratio of two data points, I get to cancel out that rate constant K, which is great because I don't know K. Okay? But by strategically picking these two data points here, where the concentration of the nitrogen dioxide also does not change, if I want to just go ahead and fill in those values here, take this same equation, but now for my first data point, I'm going to fill in the concentration, which was in from my data set, 0.2. But from my second data point, that concentration was also 0.2. Right? So let's just look closely at this expression here. What's going to happen? They're going to cancel out. So by picking a data point where those two values are the same, now I get rid of both of these terms, which is good because I can't have two variables in there and still solve. Right? So I got to get rid of m, then I can solve n. Right? So again, we're going to pick two data points, and we strategically picked these two here because the concentration of the nitrogen dioxide was not changing, but the concentration of the nitrogen carbon monoxide was changing. All right, so boom, now everything's simplified. Okay, so let me just get rid of what we crossed out here. And now I'm left with the same situation as we saw before, right? Where now I can just plug in my data. My rates for my first data point was 0.0082. And the rate for my second data point was 0.0082. Plugging in my concentration information, my first data point, carbon monoxide, was 0.1. And for my second data point, carbon monoxide, was 0.2. All right, now we'll do this a long way just to sort of make sure that we got this down. But if we're going for the speed record, just by looking at these numbers here, what is going to be the order of this reaction with respect to CO? 0. Why 0? Because the rates aren't changing, right? Regardless of the change in concentration of carbon monoxide, my rate has not changed, right? It's independent of that concentration, so I know my rate will be 0 here. Okay, but we can do it the long way mathematically. How would we solve this? We can just sort of simplify here on this side, on the left. What's going on? Don't you freeze on me. On the left, what's 0.0082 divided by 0.0082? 1. Technical difficulties, hold on. Let's just go ahead and turn it off and turn it back on again. Okay, so this would be 1. 0.1 divided by 0.2, we can sort of punch it into our calculator as 1/2, or 0.5. to the power of n. Oh, I guess just to be clear, I simplified this by pulling out that exponent, 0.10 divided by 0.20. Same thing. Okay? And then I need to pull n down from that exponent, so I'm going to take the log of both sides. So then this is equal to n times the log of 1/2 equals the log of 1. So then I can solve for n by dividing both sides by that log of 1/2. All right, and you can go ahead and punch this into your calculator to convince yourselves, but you would get that n is equal to 0. All right. So going back up to my rate expression here, we said that this was our goal to find. We found one of these two, right? We know what n is now. To find m, we're just going to have to grab another 2 data points. All right. I'm going to label these A, B, C, and D. All right, and I want you to take a careful look and decide which 2 data points you're going to select for this next calculation. right? Remember when we first selected, we did these two because this was not changing and this was. So now we need the opposite strategy. All right, and there's actually three. You could pick any combination of these three and it would work. But A, B, and D all have the same concentration of carbon monoxide. So if I pick any combination of those two, I would get the correct answer for M. Right? A and B, A and D, D and B, either one, any one of those would work because in those cases, my concentration of carbon monoxide is not changing and my nitrogen dioxide is. Okay? So for the sake of all being on the same page, let's just pick A and B. And I want y'all to take a minute and tell me what the order of this reaction with respect to the nitrogen dioxide is based on these two data points. I want you to do this calculation yourselves. What's up?
Can we not use the same two data points but plugging in the zero order into the original defined them after?
You wouldn't. Maybe. K cancels out. 0.2, 0.2, point. Yeah, maybe. I don't know. That's not what we're going to do. Let me think about that. No, because you would get m1 to the power of m, which is always just 1. So that term, that it effectively nullifies your ability to solve for m, because 1 to the power of anything is just 1.
Right.
So m it ends up dropping out of this equation, and we can't solve for m anymore. All right, so again, by selectively picking these concentrations where my carbon monoxide is held constant, that cancels out along with K. So my ratio of my rate expressions just becomes this. So then I can plug in my data. All right. My concentration data then, 0.10 to the power of m, 0.20 to the power of m. Can pull out that m. Okay. So then I'm going to take the log of both sides. All right, and then to solve for m, I'm going to, let me get rid of this. To solve for m, I'm going to divide both sides by that log of 1/2. Okay, that'll cancel this out over here. All right, and then punching that into my calculator, I get 1.965 and some change. That's because this was real data that was collected, and so sometimes it doesn't always work out to be nice, neat, whole numbers because of real data, because of the error that's incurred with any measurement that you make. For the purposes of our pencil and paper chemistry, we'll sort of always have it work out to be nice and neat so that we can get a whole number. What do we think 1.96 is in terms of a whole number? 2, right? So we have our goal was to find our rate expression here, the orders, and we found that m is a second order with respect to the nitrogen dioxide. Okay? So there's 2 more things that I can ask you from this type of problem here. All right, let's just get rid of this here because now we've got our order figured out. Now I actually have enough information to solve for my rate constant here. Get the value of my rate constant. All right, which data point, A, B, C, or D, am I going to pick to figure out what K is? What is it? Any of them, exactly. It doesn't matter at this point, right? I got all those pieces. As long as I have those orders, it doesn't matter because I'll have a concentration of nitrogen dioxide, a concentration of carbon monoxide, and a rate for any one of these data points. So I could just pick one of them and roll with it, plug in my variables, and my only thing missing will be K. So for the sake of all being on the same page, let's just pick this first data point. My rate is this 0.0021. Plugging in my data for that first data point, the concentration of nitrogen dioxide is 0.10 squared because we established that it was second order with respect to that reactant. And then this is just going to be 0 because anything to the power of 0, oh, it's just going to be 1 rather, because anything to the power of 0 is 1, but nonetheless we can put it in there. All right, and then how are we going to get K all by itself? Just sort of simple algebra of rearranging. Divide both sides in order to move all this over. So then K is equal to 0.0021 divided by 0.1 squared, or 0.21. All right, so again, our original expression here, we had a bunch of missing things. We had our rate constant that was missing, and the order of these reactions. All right, and using this initial rate data, we were able to fill in this entire expression here. Now we have our orders as well as our value of K. So now we can predict the rate of this reaction at any concentration of reactant, right? We can make this number anything and this number anything and figure out what the rate would be. Okay? There's one other thing that we can do now that we know the order of this reaction here. Let's just go to a new page here. And this is figure out the units of that rate constant K. All right. The units of K are dependent on your reaction and the order of that reaction. It's not always the same. We don't always have the same units for K. What we do always have is the same units for the rate of a reaction. Okay? Rates are always measured in big M. What's big M stand for? Molarity per second. We do not know the units of K. So what we're going to do is kind of just fill these in with these units as if they were variables here. We don't know the units of K. That's what we're going to solve for. All right, but we do know the units of our concentration. What are concentrations measured in? Molarity, right? So this first is molarity squared times molarity to the power of 0. All right, and if you don't already know from algebra class, just convince yourself with your calculator right now. Punch in any number, punch in your birthday and raise it to the power of 0. The power of any number raised to the power of 0 is just 1. Right, so from this here, so I'm just going to get rid of it because it's 1. All right, so from this here, everybody take a second and rearrange and tell me what the units of K would be for this particular reaction. All right, you're solving for K in the same way that we would solve for it if these were numbers, right? You're going to get K all by itself by moving everything else to the other side and then simplify. All right, if I'm going to get K all by itself, I'm going to divide both sides by molarity squared. So this becomes M over M squared per second. So how should I simplify this? I'm going to be able to get rid of one of those M's, right? This one's going to cancel with one of those. So my units of K are 1 over molar second. All All right, and just to be a pain in the butt, and really because it's easier to enter in on a computer, you would see this same thing as M inverse 1, S inverse 1. These are all the same. These are one and the same thing. Right? To be clear, 1 over x is the same thing as x to the negative 1. All right, algebraically speaking. Cool? All right, so again, from this initial rate data, right, that's our goal, is to take a data table like this and analyze it to find, and we can do a few things here. We can find the order of the reaction with respect to those reactants. Again, we got to be strategic with the data points we pick. Once we get the order, we can find that rate constant K and the units for that rate constant K. All right, so from this data right here, we can do quite a bit in terms of being able to predict what's going to happen to the rate for any concentration of reactant. All right. So the next thing we're going to do, these are what are called the integrated rate laws. All right, so for a 0th order reaction, we said that the rate was equal to some constant K times the concentration of A to the power of 0. All right. And then, of course, if it's A to the power of 0, what does that simplify to? 1, so this just becomes K, right? But if we're going to do like some fancy sort of calculus here, our rate is dA over dt, and since it's a reactant, it's negative. All right, so integrated rate laws are now we're going to integrate this equation, but this isn't a calculus class, so you're just going to friggin' trust me on what the answer is, all right? If we take this and we integrate this with respect to dt, we now get a new equation, which is our integrated rate law for a 0th order reaction, that gives us the concentration of that reactant as a function of time, which for a 0th order reaction is equal to negative kT plus that constant C, right, because it's integration, which in this case would be the initial concentration of reactant. All right, so to be clear, what this is saying is this is the concentration of A as a function of time. Right? So if we do all that work and we figure out from that initial rate data what our constant is, what our rate constant is, then all of a sudden we can predict what's going to happen to the concentration of A at any point in the future, right? That's what this function is going to do for us. If we know K, then we can plug in any time and figure out what the concentration of A will be. That's what this equation is. Okay, so just for the sake of practice here, let's say that the concentration of A initially is 1 molar, And our rate constant K has a value of, let's use that value that we just solved for, 0.21. What is the concentration of A after 45 seconds? Okay, everybody take a second and see if you can't utilize our new integrated rate law to figure out what the concentration of A would be. And before you do that, we're going to actually do it just after 2 seconds. Don't do 45. We'll do 45 here in a second, and we'll explain why that's not going to work too well. Okay, so we'll do it after 2 seconds. All right, so all we're going to do is plug in our variables. I guess just to be clear, right, because this thing over on the left-hand side looks kind of funny. This is just like f of t, right? That's how we write our functions. Concentration of A as a function of time. So I'm going to plug this into my equation. A function of time is negative 0.21 times t, which is 2 seconds, plus my 1 molar, and I get a concentration of now 0.58 molar after 2 seconds. So my reaction's already about halfway done at this point. Right, but you can then predict for any point in the future what your concentration of A would be. Now, because this is a 0th order reaction, and I think that everybody hopefully can see just by this equation here, it's going to be linear with respect to time, right? A straight line. So if we were to sort of make this plot, let's go back to... If we were to plot reactant, so we're looking over here now. If we were looking at reactant concentration versus time for a 0th order reaction, it's linear with the slope of negative k. So it just kind of crashes down, right? Now, if you did plug in 45 to that equation that we had before, what would you get? Did anybody do it? A negative number, right? Which makes no sense at all, right? You can't have a negative concentration. That just means that your concentration of A is already 0 at that point, right? It's already crashed down to that line and then just kind of flat lines from here. But you can't have a negative concentration, okay? So if you do get a negative number, it simply means all your reactant has been consumed. All right, so to finish this up, so just to be clear, let's summarize. We said for a 0th order reaction, we have this new integrated rate law. So then let's look at what it would be for a 1st order reaction. and a second order reaction. All right, and then for those of you in calculus, it can be a fun little exercise to do on your own, but y'all are just going to trust me here. For a first order reaction, the concentration of A changes as a function of time, where it's the initial concentration times e to the negative kt, that magical number e that appears in calculus a lot. All right, this is what would be called an exponential decay. And for a second order reaction, if we played the same game, integrated a second order rate equation with respect to t, we would get the following. Oops. All right, now, these will all be given to you on your constants page. You just have to know how to use them and really what they're saying. Again, these integrated rate laws allow us to predict how the concentration of A changes over time. All right, if we do that hard work, we take that initial rate data and we solve for that rate constant K. Now we can predict what would happen to the concentration of reactant over time. Cool. All right, we'll pick up with this next time.